Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss current for step junction. Let's begin. In order to calculate current for step junction, we have to consider a step junction, step graded PN junction. PN junction categorized as step graded or linearly graded on the basis of their doping. Here P type semiconductor, N type semiconductor, and it is a step graded PN junction, means the doping we used in that of junction the doping are used in that of P type or N type towards that of junction is constant. That is why we call it as step graded PN junction. Here we consider a step junction. That is the step junction. A step graded PN junction. That with the depletion region from x1 to x2. We do not apply any kind of external electric field. Therefore, throughout that of depletion region, or we can say throughout that of junction, no current flow, that is the open circuited. Write it in the open circuit PN junction, the current must be 0. As there will be no flow of current throughout that of junction, the current density for electron will be 0. The expression for current density due to electron, that is the combination of current due to drift velocity and current due to diffusion due to drift velocity, that is E n mu E into E, electronic charge n, density of free electrons mu E, mobility of electrons E, applied external electric field, plus due to diffusion E dE dN by dx is equal to 0. Electronic charge d of E and the diffusion constant, that for electron dN by dx, at the gradient how the number of electron density vary with the distance. Which implies E dE dN by dx, that term to this side, minus E n mu E E, which implies dN by dx is equal to minus mu E divided by dE E dx. Here we can use Einstein relation for diffusion constant. Let equation number 1. Einstein relation for the diffusion constant. D and mobility mu, that is diffusion constant to mobility is equal to kT by E, whereas K Boltzmann's constant, T absolute temperature. Therefore, for electron as well as holes, we write it dE by mu E, diffusion constant for electron to that of mobility of electron, is equal to d of H, diffusion constant for holes, mobility of holes mu of H is equal to kT by E. Let equation number 2. Now we can use that equation number 2 in that of equation number 1, using equation number 2 in equation number 1, we get it is dN by N, dN by N, the dx is multiplied that side. Okay. So dN by N is equal to minus E by kT E dx, as I put that value in that of equation number 1, and integrating this equation across the junction from x1 to x2, that is known as the transition region. That region x1 from x2, we integrate it. So integration of dN by N, the density of electrons it is from p type to n type. Therefore, density of electrons in p type, density of electrons in n type is equal to E divided by kT, that integration from here x1 to x2 minus E dx. Here the term integration over x1 to x2 minus E dx, that is nothing but barrier potential, or dn by n integration as log of n base E using the limit np nn is equal to E by kT Vb, where Vb is equal to integration from x1 to x2 minus E dx, which is one called barrier potential. That is the relation of potential to that of electric field. Using upper limit and lower limit, log nn base E minus log np base E is equal to E Vb divided by kT, or log A minus log B, log of A by B, log of nn divided by np of base E is equal to E Vb divided by kT, or the ratio of nn divided by np, that log to this side it will be exponential e to the power E Vb divided by kT, that is the exponential, but that one is charge of electron, not confused. Equation number 4, that is the ratio of electron density at the depletion region in n region. Here is the electron density at the depletion region in that of p region. So, I write it nn electron density at depletion region in n region, n type semiconductor region. Similarly, n of p is the electron density at depletion region in p region. We get that type of equation taking as J of E is equal to 0. Similarly, at that of same condition, when we treat it as in open circuited situation, J of S will be 0. Similarly, if J of S will be 0, then we get the expression as P of P divided by P of N is equal to e to the power E Vb by kT. That is equation number 5, where P of P the whole density at depletion region in p type, in p region, depletion region in p region. Similarly, p of n, that is the hole density at a depletion region in n region. These two equations we get when we treat with open circuited PN junction. Open circuited PN junction, that PN junction is a step graded PN junction. Another situation, in that particular situation there will be no such flow of current, but when we apply an external electric field or external potential is applied to that of PN junction, and that to be forward bias situation, then current flow through that of junction. In reverse bias situation, no such current flow. Let me take it. That PN junction the step graded PN junction it is forward biased. P type is connected to positive terminal, N type is connected to that of negative terminal. Positive, negative potential, current flow, free electrons move towards P type and holes in that of P type towards that of N region. And the PN junction with forward potential applied. Since a small potential V is applied to that of junction with positive terminal to P type, negative terminal to N type, that is the forward bias situation, then the junction barrier potential is reduced, barrier potential VB minus applied external potential V. As a result, with a forward voltage V that is applied to P type, the barrier potential is reduced to VB minus V. Therefore, the hole density on the n region of the junction becomes this Pn plus del Pn which is equal to okay. First we have to calculate what is Pn. In these two equations, here Pn can be calculated as P of P e to the power minus EVB divided by KT. Similarly, here n of P is calculated as n of n e to the power minus EVB divided by KT. These two equations are needed to us. We add del Pn towards that of Pn. In this way, that expression will be changed to P of P e to the power minus E by KT, that potential change to Vb minus V, that potential change to Vb minus B. Okay, change in that whole density in the P region. Therefore, P of n plus del Pn is equal to, expanding that one, so P of P e to the power minus EVB by KT into e to the power EV by KT, or del Pn is equal to P of P e to the power minus EVB by KT e to the power EV by KT minus Pn. Here we have to put the value of Pn. The value of Pn is put here. Therefore, del Pn is equal to P of P e to the power minus EVB by KT into e to the power EV by KT minus Pn value as P of P e to the power minus EVB by KT, or del Pn is equal to P of P e to the power minus EVB divided by KT, that is the common term. That a bracket we have e to the power EV by Kt minus 1. The equation number 6. Similarly, when we take that equation and calculate taking with a forward voltage V to N type, the barrier potential is reduced to Vb minus B, Vb minus V, and the electron density on the left face of the junction, that is P region, becomes Np plus delta Np is equal to, use the value of Np as this much, Nn e to the power minus E by Kt. Here the potential reduced to Vb minus V, or Np plus del Np, that can be expanded Nn e to the power minus EVB by Kt e to the power V by Kt, or del Np is equal to Nn e to the power minus EV by Kt e to the power V by Kt minus Np. Now the value of Np is put here, or delta Np is equal to Nn e to the power minus EVB by Kt will into e to the power V by Kt minus value of Np, Nn e to the power minus EVB by Kt, Nn e to the power minus EVB by Kt, or delta Np is equal to Nn e to the power minus EVB by Kt. Taking as common, inside that bracket we have e to the power EV by Kt minus 1. Equation number 7. Now we have del Pn and del Nn, del Np, as we apply some external potential to that of step graded PN junction. Therefore, a current flow through that of PN junction. Now, what be that current? Let me calculate it. Therefore, the total current across the junction is I is equal to current density into area. A, the junction area. J, current density is equal to current per area. So, current is equal to current density into area. Let we apply the expression for current density, or I is equal to expression for current density. So, A, current density expression E del NP VE plus del PN VH, that we have already known in case of conductivity and mobility of semiconductors. So, putting the value of del Pn and del NP and del Pn values are put here. We have I is equal to A E NN VE plus PP VH e to the power minus EVB by KT. First we put that of value and then that term treated as common, e to the power EV by KT minus 1. That entire term is known as I of S into e to the power EV by KT minus 1. That is the expression for this is the expression for current of step junction, current for step junction, current for step junction. It is also known as PN-DIODE equation. PN-DIODE equation. And IS, I of S, that is A E N N V E plus P N V S, V E drift velocity of electron, V S drift velocity of holes. We have already known it, e to the power minus EVB by KT. That current, the reverse saturation current, reverse saturation current, reverse saturation current. Here, with the help of this video lecture, we understand the concept of current for step junction. First, we take a step graded PN junction without applying any external potential. At that of situation, we evaluate NN by NP. From this, what is NP? Next, PP by PN. From this, PN. Again, we apply external potential to that of PN junction, that PN junction is forward biased, then that expression changes to this way del Pn, next del Np, and finally total current across the junction, the value of J, and we put the expression for del Np and del Pn taking the common. Finally, that equation is nothing but the expression for current for step junction, which is also known as PN-DIODE equation, and I of S, which is reverse saturation current. So, with this useful and informative notes, let me wind up this session. Thank you.